Good day, everybody. I'm Eddie. We have Anson and Zihong. We are from Group 2, and we are very excited to present to you the Water
Water Walker.
Walker. The challenge presented to us was to design a water walking vehicle with bio-inspired locomotion that can navigate on a water surface through designated routes in a water tank. Some of the design challenges include: first, for the vehicle, it must have biological locomotion. The main body must always be above water. It must have equal to or more than four legs with periodical contact with water surface. And all the electronics and control systems and battery must be on board without any umbilical cable. As for the function, it must navigate through designated routes, autonomously maneuver without active user control during the performance, and finally, route around device gates without contact.
Looking back at our Gen 1 Water Walker that we did based on initial literature review in January to March of 2022, the design is inspired by the Water Strider robot, Basilisk Lizard, and Spike the robot dog. The body frame and legs were to be manufactured by 2020 aluminum extrusions, while the feet, body coverings, and joints were to be 3D printed using PLA. The size was approximately 300 times 207 times 222 mm. MG90S microservo motor is used as the driving motor, and Arduino Uno board is the only PCB as controller of servo motor. Lastly, the turning principle was to tune the motor speed of each leg. This slide shows the Water Walker Gen 2 that we did for the September to December 2022. On the left, you can see the CAD model of our Water Walker, and on the right, it is the actual model of our Water Walker that we tested on a pool.
Water Walker has been segregated into four main subsystems, which is body, locomotions, electrical hardware, and control systems. Eddie will be in charge of the Water Walker body, which includes body, legs, and feet, as well as other miscellaneous items like fasteners and bearings. And for the locomotions, it's supposed to be in charge by our previous groupmate, Jaden Lam, but due to some unforeseen circumstances, he will be dropping out and I will take over his task. Therefore, I will oversee electrical hardware along with locomotions. Electrical hardware includes battery, servo motors, and controllers. And finally, Zehong will be assigned to control systems that perform coding of power supply, initial positions, turning, and movement angle.
In this section, we will be showing the controlling component used in the system, our latest control system design, and the modifications from the Gen 1 Water Walker. Arduino Uno R3 is the main microcontroller used for the entire subsystem. It acts as the brain of controlling the movement of the Water Walker. Also, an 8-channel servo controller chute is newly introduced to supply more voltage to power all the servo motors. It is designed to control 8 independent servo motors concurrently in a single board with a built-in 5V 5A switching regulator. Then, servo motors model MG90S is selected to be the driving motors of the Water Walker, and lastly, a 2-pin rocker switch is used as the on-off switch of the subsystem. In our latest control system design, the Arduino Uno board contains all the program inputs to the servo chute, servo motors, and rocker switch. Servo motors and switch will not directly connect to the Arduino board. Instead, servo chute is attached to the Arduino Uno board to receive the input from Arduino. They are driven by 2 different power sources and will be explained later in the electrical subsystem by Anson. Then, the servo chute controls the 5 servo motors and rocker switch. The servo motors are attached to channel 1 to 5 of the servo chute accordingly to the order as shown. For motor movement, all motors have the same initial position at step 4000. approximately 90 degrees. Left and right half of the legs cause the motors to have different movement position. Left motors are moved from step 3000 to 8000, while right motors are moved from step 5000 to 0. The movements are completed in 1 second. The principle of the motors such that the water walker can move smoothly is that one pair of diagonal legs will move while the other pair will not move. For example, front left and rear right motors will move first, followed by front right and rear left motors. For turning movement, the turning motor has an initial position of step 0. To fully utilize the motor on the timing belt, it moves from step 0 to 8000, or reversely in 1 second. The control principle is that the water walker will travel for X seconds before reaching the gate. After X seconds, turning motor is activated for 5 seconds and then reversed for 5 seconds to travel back at a straight path. This principle applies to the water walker every time it needs to turn. Besides, a switch is added to start the motors on or to shut them off. To conclude the control subsystem, the Gen 2 version has 5 motors that are powered by a servo shield. The new 5th servo motor is in charging of the turning, which is different from the Gen 1 steering mechanism. An on-off switch is also added to control the flow of power to the servo motors. In the progress of achieving the Gen 2 system, we have looked into the possibilities of using two Arduino Uno as inputs, push button and potentiometer as switch, and tested the power supply.
Therefore, all these components we need to review and modify based on their challenge phase. This system includes battery to power up, motor to move or steer the legs, and program circuit board to act as the brain of the system. All of these components selected will be discussed later regarding the design and justifications. Finally, the placements of components will then assembly to another subsystem and perform a final test run. Firstly, the motors will be focusing on the theoretical calculations and final selections based on the mass of legs of water walker. Buoyancy force that helps to lift up water walker will be discussed on later parts by Eddie, while propulsion force to move water walker forward is determined by the mass of legs. Starting from that parameters, minimum sled impulse generated by the legs is calculated by multiplying the weights of legs along with the period of motor rotates. Then, the foot velocity is determined using the formula as shown on the right. Finally, the desired operating speed is then calculated by dividing impact velocity along with the linked length that provided by body and legs subsystem. Therefore, with the final required operating speed of 0.127 seconds per 60 degrees, I have chosen MG90S micro servo as our thrust of motor with the operating speed of 0.08 seconds per 60 degree. It has a stored torque of 2.2 kilograms per centimeter to overcome the torque needed. And for the battery, initially only one battery was supplied with 4.8 volts to all 4 walking motors. However, we have met the problem of there is insufficient of power to run the motors. This challenge will be discussed later on the next slides. And for Programmed Circuit Board, in short for PCB, we have chosen Arduino Uno board as the brain of the servo motor. However, this PCB only allowed to supply a maximum of 5 voltage, which is only sufficient to power one single motor. Therefore, for this semester, a servo controller Uno shield has been added to resolve this issue, which will be discussed later. And now, the next video will show you what is the challenge faced previously. With 4.8 volts supply, the legs cannot move properly and cause some jerky motions. Therefore, if every motor needs to operate at full capacity, all 5 motors, including steering motors, will require 25 volts to run. With that in mind, total batteries were added up to 4 by separating one battery to power the Arduino board, while the rest will power a servo controller that directly supply 25 volts to all 5 motors. By connecting 3 9V battery in series mode, it is able to supply up to 27 volts of power. And for the modifying of PCB, function of servo controller is to provide up to 25 watts of motors and able to power up to 8 motors. This controller is compatible with Arduino board to act as a power boost on top of it and power the rest of the motor. Figure above shows the connection of Arduino board and circuit. Servo controller is mounted on top of Arduino board by slotting in the channels of servo controller on the board. Then, the codes and power supply provided to the motors are linked at the servo controller at the side. Power supply of 25 watts is connected to the servo controller while the 9-watt battery is supplied for the Arduino board. The blue cable that connects to Arduino board is used for uploading the codes of the motors via laptop. And for the configurations of electrical hardware, this will be closely designed along with body and leg subsystem. Each of the motors of the legs will be located at each of the compartments as figure above shown. The battery packs is secured at rear right side of the body, while the battery that power up the Arduino board is located at the front left to balance the weight distribution so that the center of gravity will not focus on the rear side. Now for the next video, I will be showing the test run of a single leg that the motor has enough power and torque to run the legs and foot. In this video, the power supply of 5 volts is sufficient for the motor to produce required torque and speed. Leg and foot are able to move accordingly while connected to the motor. Lastly, the final video here shows the full test run of electrical subsystem. By connecting all of these components, Arduino that coded by Zhehong is able to run all 5 motors together with desired speed. Modify power supplies and adding servo controller able to solve the issues of the motor jerkings. To conclude, it is a success when these configurations works and all motors are able to rotate according to our requirements. And now for the locomotion design of the water walker. These parts were left with some works that need to be refined and I will be in charge starting next semester. Therefore, following slides may not show full progress of the work of locomotions. This design will mainly be discussed about the propulsion systems and steering mechanism. The propulsion of water walker uses the combinations of skiing and movement of robotic dog. Since the water walker will be locomoted at water surface, the leg will move as trot at figure left shown while skiing the water backwards in order to move forward. And by that, it will prevent the leg touches the water entire time by leaving other legs. For the next video, I will be showing you the steering mechanism. This steering mechanism is controlled by the timing belt pulley that pulled by the servo motor as video shown. This motor controls the axle at the middle of water walker by connecting both pulley with the timing belt. The next video will show you how does the axle rotates and steer the water walker. By rotating the axle at the middle point, water walker will propel to the direction required based on the leg's movement. For example, if body inclines to the left, the legs will propel to the right side. However, this steering mechanism cannot be done this semester due to the absence of previous groupmate. It will further develop on our future plan.
The design of our water walker body is highly dependent on the other subsystems. Therefore, the following design sequence was employed. The fasteners and bearings were selected first with the requirement by other subsystems, followed by the body containing all the components, 4 biolocomotive legs, and 4 buoyant feet sized based on the weight and dimension of the water walker. In the previous semester, the progress of this subsystem was up until the development of links and joints. The leg links were decided to be made with 2020 aluminum extrusions supported by customized PLA joints. Some scaled-down modular test components were also developed in order to test the functionality of the design without wasting materials. Finally, the fasteners, fittings, and bearing sizes were set, but a decision was later made to switch all the body components into PLA printed parts for weight reduction. The fasteners used in this project are all stainless steel unless stated otherwise, because it does not rust. The list of fasteners and bearings used can be seen on the left side of the screen. Generally, M4 was used for load-bearing parts because it has adequate strength while having considerably low mass, while M2.5 was selected for non-load-bearing parts as it is the smallest size available. The usage of fasteners of the same size across a design had proven to be convenient. However, Some standard parts in the water walker, such as the Arduino board, the servo motors, the steering and propulsion system, would require different sizes of fasteners, which is unavoidable and had to be designed accordingly. With all the fasteners and bearing size determined, the body could now be designed. It has to accommodate and waterproof all of the components on board. Therefore, PLA was our choice of material. The body was split into 4 modular compartments for the ease of manufacturing, weight distribution, and also to serve the propulsion and steering system. The components within each of the compartments were explained by Anton previously. The compartment covers were also custom developed with flexible conduit and tunnels to enable waterproof wiring connections between the body. The servo motors were mounted in the compartments with custom designed motor mounts. The assembly can be seen in the middle of your screen. The 4 batteries used were split into 3 and 1 with customized battery mounts supporting the battery holder before securing into the body. The motor coupler axle leg sub-assembly is assembled as demonstrated. With all the customized components listed, it is now time to look at the components assembly, starting with the front left and rear left. And the front right and rear right. The legs are arguably the most prominent feature of the water walker, as it stands out among other aquatic vehicles. Our water walker legs were designed according to the body length and height ratio from a variety of terrestrial mammals and robots, but it is preferred to be shorter for stability. Following that point, the dimensions selected for our leg are 175 mm in height and 10 mm in thickness. It is made out of 2 120 mm links at 135 degrees to mimic the leg motion of the references in the previous slides. Distribute the stress from the mounting point and also additional cookie points for aesthetics. The length-height ratio is 1.68, which resembles most of the references previously. With the leg design printed, an experimental compression test was done, and it could withstand at least 40 newtons of direct compressive load. FEA simulations were also performed with an approximated model of 0.8 mm wall thickness with no infill microstructure assumed. Based on the ultimate tensile strength of PLA between 30 to 35 megapascal, the water walker's leg is theoretically able to sustain 67 to 79 newtons of direct compressive load, which is more than sufficient based on the water walker's weight, which will be elaborated in the following sections. Last but not least, the feet. It is a reverse camber aerofoil shape to reduce the coefficient of drag by 90% compared to a flat incident surface. Inspiration was taken from jet ski, snowboard, and surfboards with similar front to rear curvature for drag reduction. The feet has to be designed for maximum buoyancy so that the water walker floats all the time. The design is constrained by the weight capacity and the width of the water walker. It was also assumed that point load was applied perpendicularly onto the feet, and at least 2 alternative feet are in contact with the water simultaneously during locomotion. Following that, the total weight of the body, legs, and components are 628 grams. The targeted weight capacity is therefore selected to be at 1,500 grams, with extra allowance being for the feet's weight and additional components if required. Here is how the feet volume is calculated. The minimum volume of water walker can be found from the division of minimum buoyant force and water density. The minimum volume is divided by 2, as 2 is the number of feet that will be afloat at any given time. Based on the required volume for each foot and the desired factor of safety, this dimension and design of feet was concluded with a maximum body capacity of 1.90 kilograms. There it is, the final design of the water walker, Generation 2. The total weight is 1,093 grams, which is only 57.5% of the maximum capacity. Some floating tests were done after the final assembly. The first video on your left, the single unloaded leg, floats very well. It also worked in shallow waters, but in deeper water with stronger water currents and waves in the right, the water walker was unable to stand afloat due to unpredictable directions of buoyant forces. The loose linkages also made the water walker unstable.
In this semester, all of our subsystems have satisfied 4 checklists. However, there are 2 functions of WaterWalker that needed to be developed and designed on our future plans.
Following our progress this semester, we will be assembling and integrating all of the subsystems into the main system and to fulfill the rest of the unfinished requirements in the previous slide. The work schedule and the list of tasks are listed in this slide. There we have it, everybody, the Water Walker. Thank you all for listening, and may Water Walker be a success.